All right. Well, with that, it is time to get ready for our last talk of the day. So I'm excited to welcome Sean McQuillan to the conference. Welcome, Sean.
Hey, great to be here. Super excited that we get to have this year. I know it was quite a event this spring, rescheduling and figuring out to turn it into a virtual conference. So I want to just huge call out to the organizers of putting this together.
Yeah, that was all John. It was crazy and hectic, I'm sure, for everyone. But yeah, I'm so glad that we get to have the conference and that you're still able to be here. Really looking forward to this talk. So Sean's going to be talking about performance in a Kotlin world. So with that, I'll let you take it away. And just a reminder, if you have any questions for Sean, please leave them in the Slack channel. You can find it under day3_Sean McQuillan. And with that, it's all yours.
Thank you, Ryan. Yeah, so today I'm going to be talking about performance in a Kotlin world. And before we get started, I wanted to do a call out for the hidden hero of this talk. My spouse is currently watching our toddler, which is good news and bad news. Good news, we won't have a toddler interrupt the talk. Bad news, we won't have a toddler interrupt the talk. With that, let's go ahead and get started. So I want to start off by talking about some performance best practices. And I put that in quotes for a reason. So there's one thing that I see a lot of people do, and I've done this myself, when trying to make code performant, is just to read a blog post and then apply random code that you read about online. And this sometimes works. Sometimes there's some good performance tips in there, but sometimes it actually just makes your code more complex and either keeps the performance the same or actually makes it worse. Another thing that is maybe a thing you might do with performance is use big O complexity to analyze the performance of your application and then try to improve it. So this typically doesn't work in mobile applications. If you kind of take a look at a typical mobile application, it would be the big O complexity of the application plus the database plus the network. And if we do a big O analysis like we learned about in school, we would just put those letters that are the same together and put a squared on them. And then to optimize this, we would just kind of think really hard and figure out how to turn that 3 into a 2. And this doesn't tend to be a very practical way to actually improve the performance of an Android application. And why is that? That's because the data sets we're dealing with on Android tend to be quite a bit smaller than this asymptotic complexity that big O analysis does. We tend to be dealing with 100 or 1,000 items in our data sets. And if we take a look at n equals 100, you probably saw a chart like this if you learned big O in a computer science degree, where you saw the number of operations goes up from 7 to 700 to 70,000 as you go from O of 1 to O of n to O of n squared. But if we look at this in terms of wall clock time, this might actually just be 1 microsecond to a tenth of a millisecond up to 10 milliseconds. And 10 milliseconds is quite a bit longer than 1 microsecond. But it's still, kind of a reasonable amount of time in a user-facing application. As a user, I'm not really aware of 10 milliseconds passing. That's maybe work I want to move to a background thread, but it's not so long that it's going to delay my UI. So there's really 2 main use cases for big O complexity in your adult life. The first is if you're getting a computer science degree, super important, absolutely study big O notation and learn how to do big O analysis. And the other very important time to use big O notation is during the Google interview process. I highly recommend brushing up on big O notation if you do a Google interview as well. And then a third thing for performance, this is one that I often fall in the trap of, is just kind of looking at some code and thinking really hard, going, I know how this programming language works. I know how the CPU works. I have a pretty good understanding of how the caches work. And if I kind of just think really hard, I'm going to come up with a better algorithm that's going to be able to run more performantly on this mobile device. And this typically, and I've learned this a lot, especially working at Google with some of the framework engineers that I work with, typically the code that I produce from trying to think really hard is actually slower for subtle ways that aren't really obvious as you're kind of analyzing just the code itself. So how do you do performance? So there's basically, before we jump in, there's 2 reasons that you would do performance on a mobile application. You could be doing it for work, and we call this performance engineering, and we could be doing it for fun, and we call this performance golf, which is also a very fun hobby and one that I personally quite enjoy. But either way, there's one algorithm to be doing performance optimization, and that is to define a goal. And this is a really important part. You have to have something that you're actually trying to optimize, some way to know when you're done optimizing. Then get a measurement of the software that you would like to optimize. Then you should make a hypothesis and change something, and then go back and measure again to see if you've actually improved or regressed the performance of your application. And this is kind of the key point. The big thing I want you to take away from this talk is if you're not measuring, you're not doing performance. So let's shift gears a little bit and talk about how to measure. So for the rest of this talk, I'm going to talk quite a bit about how to use the Android Studio profiler. And then I'm going to talk a little bit about how to use the benchmarking library to enable consistent performance. So starting with the profiler, let's jump in and take a look at the profiler. So in order to run the profiler, I'm just going to use sorry, that was a video. I'm going to use the profile button up on the Android Studio toolbar. It's just to the right of the run button. And when I do that, it's going to load up the profiler. And when the profiler runs, it's going to initially display kind of this overview screen, which is actually surprisingly useful for getting like this high-level overview of what your application is doing. So it's going to, at the very top there, it's going to display activities or fragments that are being displayed. And it's also going to display the current CPU usage of your application. And this can be a really good way to get a quick indication that there's something going on. Maybe your application's not actually doing anything, but it's still using 40% CPU. That's something you would want to dive into further. That also tracks memory allocations and shows you the memory usage of your application, which is something that's incredibly useful at a glance. Basically, if you see this going up and to the right as you use your application, you have something going on that you need to go in and dig a little bit more into the heap dumps and try to figure out what's going on. It shows network requests in your applications as well. So this is going to show on this display just the number of network requests that you make. And if you click in there, you actually get something similar to the Chrome inspector that lets you take a look at each of the network requests themselves. And then down at the bottom, there's this thing. It's really interesting. It's this energy profiler. And it's something that it's a little bit weird, honestly. It's a bunch of heuristics that we've come up with that tend to be indicative of poor energy usage. So when you see this go up higher on this bar here, that means that by these heuristics, CPU, network, that sort of thing, the app is using more energy. So if you see this very high, especially when your application's at rest, this is indicative of something that you should go dive into more and take a look in there and see what the heuristic that is causing the energy to be used. So there's a couple things as we start actually using the application. The profiler is going to show us the touch events with those red lines up there on the top. And then you can actually see this is all like aligned on the same y-axis here. You can see how the touch events caused a little CPU usage because they actually had to, draw the list as it was scrolling. So this is really, really useful for seeing like when I touched the screen and I did this action, what was the effect on the overall system performance. Then I'm going to also be able to do a navigation. And this is a compose application, so I'm going to stay in the same activity. But I'm going to see here that the memory usage went up a little bit when I did this navigation. And this is because I loaded this larger bitmap, and I also parsed that fairly complex string right there. And then I can continue on this user journey here, and I can see that the back is represented up top as well. And if I take a look at the memory really, really closely, it's kind of hard to see on video, I'm sure. But if I take a look at that memory right there, I can see a little bit of a dip as the screen that was using a lot of the memory was actually garbage collected. So this actually looks really healthy. Now, I want to stop here and say, I profiled a compose application at the beginning of this talk because I was hoping to find a performance problem in one of our compose samples that I could then work through and show how to solve. But I was actually unable to find one. So I'm going to switch gears and switch over to a view system application, IOSchedule, that does have some performance problems that are going to be easy to find with the profilers. So next up, I want to talk a lot about the CPU profiler. The memory profiler, the energy profiler, and the network profiler are super useful when you have specific questions that are answered by those profilers. But typically when you're profiling, the profiler you're going to spend most of your time in is the CPU profiler. And it helps you answer the question, what was my application doing that caused it to take so much time? So it's a really, really good tool, and it should be your like go-to tool if you find a screen is taking maybe 2 seconds to load, but you expected it to take a couple milliseconds. CPU Profiler is your tool for that. So for this, I'm going to get a bug report that's going to come from a App Store review that's saying, why does this app take so long to launch? And our product manager took a look at it and filed a bug. The bug's just the title, slow startup, and the entire description is seems slow sometimes, which I'm not super jazzed about as a bug report. The sometimes there tells me this is going to be maybe a more tricky thing to track down. But I'm kind of thinking about this, and based on prior experience profiling Android applications, what I'm hearing when I hear that startup is slow sometimes is the most likely culprit there is the slow start or application on create process is itself slow. And then the product manager may be backgrounding the application and then relaunching it, which can skip the application on create path, which when that happens, that's indicative that the application on create is taking too long. So to debug that, I'm going to use the profiler as well. So I'm going to use the edit configuration option, and then I can go over to this profiler tab, and I can start recording at startup. This allows me to start doing CPU recordings at startup. So I can use that CPU tab from the very moment my application launches, and this will let me capture that application on create in the profiler. So I'm going to click that on, and then I have a couple options here. I can sample Java methods or I can trace Java methods. And the difference between these is a little bit subtle. So sample Java methods basically means every, there's a poll that launches maybe every like 10 nanoseconds that checks what function is running and keeps track of it. Whereas trace Java methods is actually going to instrument every single Java method so that every single entry and exit of a Java method gets noted. It's quite a bit slower, and it generates a much larger trace file. But I'm going to use it for this video because it led to a prettier trace on the screen. There's also C++ sampling and system calls. So C++ allows you to sample native code, and tracing system calls allows you basically to run systrace. So you, instead of seeing the actual Java method you're calling, you're seeing your interactions with the framework. So you're going to see things like a recycler view paint event as something that you're going to see there. So I'm going to click on trace Java methods, hit OK, and then I'll launch the profiler with the profile button up here. And then once I do that, Android Studio is going to open up the profiler pane. There's one trick to the profiler pane. You'll see as we go through this, the profiler has a pretty large UX, and it originally displays in a small bottom pane. I highly recommend pulling it out. You can just use the gear icon on that pane to configure it and say that you'd like it to be in window mode. And once you do that, you can make it a standalone window, and I often put it on a second monitor when I'm doing profiling related tasks. So it's going to go ahead and launch the application. And you can see there that it was tracking the CPU usage. And there's a couple things that I can already see from this display while the application was doing its launch. So I have the CPU and thread count up at the top. And I can see the CPU usage there's a little spike at the beginning, then it's pretty constant for a while. And then there's another spike again. And that's actually indicative that there might be a performance problem during that flat period, because that probably means the main thread is doing a bunch of CPU intensive work. I can also see the thread count grows as the application gets warmed up. This is pretty typical. What you kind of want to be looking for there is the thread count's constantly going up or down, or the thread count is just constantly growing. These are both indicative of some sort of performance problem as well. The other thing I can see on this display is the main thread right here is represented visually, whether it's currently doing something or whether it's idle waiting for something to happen. So the areas where they're marked in green are busy. So I can see actually there's quite a bit happening on my main thread here. So let's stop the recording and we can take a look at the trace and see what's going on. And when I get into the trace, it's going to show the entire CPU profiler UX. And this is a pretty big UX, so let's take it step by step and walk through what's in here. At the very top left, we're going to see that there is a time range, which is, again, that's that CPU performance graph that we had before. Shows a start and an end time range, and that's going to drive the rest of this UI. Then down below, it's going to have the user input, and the activities or fragments that are displayed on the screen are going to be represented in this user and lifecycle section right here. This can be useful for correlating between touch events and other things that are happening. And down below, I get this overview of threads. And this is really, really powerful because by default, you see all of the threads in your application. And then you can actually see on each thread what it was doing at a particular time. So I can see, for example, the main thread here is actually doing just a whole chunk of CPU intensive work there for a little bit where it's flat. And then it looks like it's probably rendering a bunch of views later where it's doing a bunch of spikes up and down. And what this actually is from the trace, it draws basically 1 pixel for each function call that you have in your stack trace at that point in time. So when I look at this, there's a couple other pieces of information I can get out of it. The yellow section here is the platform code, and the green section here is the application code. So that's your application code and all of the libraries that you're using in your application. I can also see the default dispatcher is doing a big chunk of work down there as well. And this is really, really interesting because I can see this is actually correlated to something that happened on the main thread. The main thread did something and then at some point kicked off some work on the default dispatcher. And this is really useful because I can see the interplay between the threads right here in this overview panel. And then over on the right, we have the analysis section. And we're going to spend a bit of time talking about the analysis section, but it's basically driven off of the current selection over on the left. And it allows you to dive into a specific analysis of a section of your profile trace. So to use all of this, what I'm going to do is I'm going to select a time range. So right now, I would like to select this time range right here, because what I want to dive into is actually what is that default dispatcher doing that's taking so long? And is that something that I need to care about? Is that something that might be indicative of some sort of performance problem? And this could happen if the UI was actually waiting on a result from that default dispatcher. So I'm going to select a time range that that captures just that default dispatcher work area. And then I can see down below that the thread is something I can select. And it's actually been updated to be just the time range that I selected up above. And then now I've selected the default dispatcher. So the analysis section changes to show the analysis for just that thread. You can see up at the top, it says default dispatcher worker 3. And by default, it gives you this longest running events, which occasionally is useful, but it's not usually the one that actually answers the question, what was this thread doing for me? Instead, there's actually these tabs down below, the summary, top-down, flame chart, bottom-up, and events that are really, really useful for diving in and answering this question, what was this thread doing, and which part of it took the most time. So with the top down, I get basically a call tree. So you can think of this as if you took all of the stack traces and put them together in a tree, you would end up with this top down view. And this is an interesting view for basically understanding if you have basically understanding what the overall stack traces of this section of code was. To be honest, I don't use it that often, but it's often useful for correlating some insight that I got from one of the other sections. The next section here that I'm going to talk about is the bottom up. So the bottom up is basically the inverse of the top down. So instead of taking and putting the top of the tree as a node and then building a tree from it, instead it takes all of the leaf nodes and puts them at the bottom, or it shows all of the leaf nodes from that tree as the top line things. This one's actually really, really useful for answering a very specific question. What function took the most time in this trace right here? So I have this self microsecond. So this is showing me when this function was called, how much time was spent in that function as opposed to a function that function called. So when I look at this, I can pretty quickly note that this section is basically just doing JSON parsing. And so that's what this entire dispatcher is doing this whole time. And that's where all of the time is going. And then the last tab I'm going to talk about during this overview section is this events tab over here. And this is just like literally everything. There's no roll-ups happening. There's no tree structure. This is literally every single function call. And this one's really, really great at answering a very specific question. If I sort by wall duration, I can often figure out what early in the stack trace was the thing that took the most time. So here I'm seeing that it's parsing the bootstrap JSON that this application uses to get the default schedule. So I want to switch over to the main thread and see what the main thread's doing. So I have this section here that's kind of indicative of a performance problem. And I need to kind of analyze the main thread. So I've already kind of ruled out the default dispatcher. It was the easy one to take a look at. Now let's look at the main thread. To do that, I'm actually going to click on this little shove right here, and I can expand out the call trace here. So this is actually all of the stack traces at the various points of time displayed as a nice little graph right here. So I can easily view what each section of the code was doing. And if I kind of dig through this and play around with it, I can actually figure out what each section of this was doing. So at the very beginning, it's just doing class loading. You're always going to have this in every application because you just have to load your classes so that you can actually run them. Then after that, there's a small bit of Firebase initialization. Then there's the 310 library, which we use for dates in this application. So 310 is going to get initialized in application on create. And so we can see that here represented in this time. And then after that, I have this whole giant section of Dagger, which is kind of interesting, and we'll take a look at that. And then once Dagger's finished, it finally goes ahead and starts the activity and then draws the screen. So this Dagger section, like what is going on here? Dagger's not particularly slow by itself, so this must be something we've done with our Dagger dependency graph. And I can answer that question pretty quickly by just looking through the calls here to see what's the longest one that's interesting. And what I'm finding is that there's actually a call to json.fromJSON in here. And exploring the code, I'm able to correlate this and see that, in fact, by walking through this stack trace, I eventually lead to a place where it's actually bootstrapping the thing that's the exact same JSON that's being read over in the background thread there. But because our dependency graph loads it eagerly, it's actually happening and blocking application on create. So the solution to this really is the same as the solution to any sort of situation where you're doing something like loading JSON and it's blocking the main thread. And that is we're going to move that to a background thread and we're going to use asynchronous loading. The actual code there is a little bit too much to show in slides. It involves quite a few classes. But this is a pretty typical, let's move some work to the background thread problem. So I promised some Kotlin. Let's switch tasks a little bit and take a look at a Kotlin related bug. I get another bug report from my product manager. This bug says that the schedule is slow, and it seems slow. And the product manager this time tells us it always seems slow, which is a party. That's amazing. I love it when things are always slow because that makes it so much easier to figure out what's going on. Now, since this is a Kotlin section, let's think about some of the things that we might be looking for in Kotlin-related performance problems. So if you've been on the internet since Kotlin came out, you might have some ideas of Kotlin gotchas that might be performance problems. So we might think that lambda allocations might be causing this performance problem. We also think that the eager behavior of map, filter, and reduce might be causing this performance problem because it actually materializes a list for every single operation. Buy lazy is also a common thing for people to look for when they think about Kotlin performance problems because it takes a lock when you use the accessor for buy lazy. And then if you're an old school Java programming language engineer, you might be very concerned about using, capital I integer and boxing your integers, which sometimes can be a performance problem, and sometimes it cannot be. And I want to say all of these things can be performance problems, but we need to go ahead and measure to find out if that's actually what's happening in this application. We're also using the entire modern Android development architecture in this application. So we have view model, live data, data binding, flows, we got the whole thing going on in here. So I might be suspicious that maybe something in here is causing this performance problem as well, because maybe I haven't tested these things and I don't know personally that they're not causing this performance problem. So for both of these, what I'm going to do is I'm going to go ahead and define the goal. I'd like to make the schedule load faster. And then I'm going to go ahead and measure to try to figure out why the schedule is loading slowly. So let's go ahead and run another profiler. This time, I'm going to go ahead and click into the schedule. And if you have a Kenai there, you can actually see that there's a very small hiccup in the animation, which is very indicative to me that is something that's blocking the main thread. So I stop that trace, and we can dive into the trace here and try to figure out what's going on when we first load the schedule. And there's definitely something going on with the main thread. So let's try to figure that out. So the first thing I want to answer is is view model live data data binding causing any of this performance problem? So I'm going to take a look at the full trace. This part here is the section that is everything from the fragment getting created up to the fragment displaying on the screen. And when I take a look at that, I can see that there's an on resume, there's an initial draw of the fragment. There's a little bit of a loading spinner. It has to do a little bit of CPU work in order to display the frames. Then it's calling this function update schedule UI, which is quite unexpected. And then after that, I have recycler view where it's going to do binding, layout, and measure and draw. So I'm going to zoom in on just that on create part here. And let's try to figure out what's happening in our fragment when it's on created. And this is where we're going to find all of those architecture components classes, and they're going to be created. So originally I have a big section of layout inflation here. This is expected. You're going to find this in most fragments. Layout inflation tends to be the majority of the work you do when you create a new fragment. Then after that, I have this little tiny sliver of data binding right here, followed by view model instantiation, followed by inflating the toolbar menu right here, then followed by live data and then date calculations. These are just some calculations that are required to display the screen. And then after that, we call fragment resume, which is actually going to do the rest of the layout measure draw pass right there. So we kind of set out, like, let's look at the architectural components classes, and we can see those right here. This is the total overhead from view model, live data, and data binding. There is one thing in here that I noticed right away I can optimize. And if this is a screen that's very important, if maybe it's my first loading screen, it's something I would very much consider optimizing. And that is this toolbar menu right here. I'm spending quite a bit of time inflating and setting up this toolbar menu when I could be deferring that work. The user doesn't need that toolbar menu immediately on opening this fragment. So the view model, live data, and data binding are all fine. Let's switch over and look for a Kotlin performance regression. So I'm going to switch over to the part where we actually show the list in the recycler view. And so when I look at this, I can see there's basically two chunks of work going on. There's update schedule UI, and then there's the recycler view layout and draw. Recycler view layout and draw actually looks fine. It's a pretty expensive operation, but it's actually drawing a lot of stuff, so that's okay. This update schedule UI is something that is very interesting because it's completely unexpected. I did not expect to find that in an Android application. So I want to dive in, and we're going to actually go ahead and start using the analysis section to figure out what is happening in here. So I go to the code, and I take a look at update schedule UI. And what I find is that it's a whole sequence of map index, distinct by, map, and to map, right? So this is using all those eager operations that we were concerned about in Kotlin. And if you're familiar with this advice, you might think each one of those is creating a new list. So that's actually probably creating a lot of overhead. But that's a theory we have. So let's get measurements and test that with the profiler. So we zoom in on this section here. And then what I can do is I can actually click on update schedule UI in this call trace right here. And when I do that, the analysis section actually switches to just update schedule UI. So no longer is it showing everything that happens in the main thread in this time window. It's only showing things that happen from the call of update schedule UI, which is a really powerful debugging tool. And when I found this UX trick, I was so excited because it saves so much time trying to get timelines right and all of that stuff. And then I'm going to click into that, and I'm going to click on this flame chart right here. So when I load the flame chart, it's going to display kind of a completely different view of the functions right here. The flame charts it's this really interesting skill, reading a flame chart that is kind of completely unique to reading flame charts. It's not something that you would know how to do unless you've done performance profiling with a profile like Android Studio. So let's kind of take a step back and talk about how to read a flame chart. So here I have a flame chart. It's main calculate, it calls sum, and it calls add. And to read this, I can see that main calculate sum is one of the call stacks that happens. And what I'm actually seeing here is not a specific call to sum. That's actually the aggregate time of all of the calls to sum along this stack trace. So every time main calls calculate, which calls sum, that's all going to get added together. And this is the aggregate time of those sum calls. And then over on the right, I can see main also directly calls sum. And that's represented differently because it's a different stack trace. So main calls sum directly here. I'm going to get the aggregate of all of those sum calls. So sum is actually called twice, and it's represented twice in this flame chart. The other thing that I can see in this flame chart is this call to calculate right here. So it has two functions it calls that then do work, and those both get aggregated. But there's also some time that's in calculate itself. There's this little hat section where there's no functions on top of it, and you can read that as the time that's actually in calculate. So let's take a look at the flame chart for update schedule UI. So I ran this trace a bunch of times and kind of got like an average to figure out where the time was actually going. And this is what I see. This is what the profiler says. Is the most expensive thing the eager list allocation from the Kotlin list operators? And the profiler says truncate to minutes is actually the most expensive work, followed by header creation, followed by converting to a time zone, followed by a very, very small amount of hash set add, iterator.next, array list.add, and pair, which is all of the work that's actually being done by these allocations that are happening by the Kotlin compiler. So the majority of the work is actually the work inside of this map, distinct by, and map. So this is something that I really want to like go back to one of those don'ts at the beginning and say, don't think really hard. Don't look at some code and be like, I have some ideas about how this programming language works. I have some ideas about how the CPU and so forth work. Instead, go get measurements and actually figure out what your application is actually doing using the profiler. And also, don't apply random code you read about online. It may or may not actually make your app faster, but it will definitely make your code more complicated. So now what I need to do is in the performance algorithm, I need to define a goal, I need to measure, and I need to change something. So here what I'm going to do is I'm going to take a look at these two things right here. Truncate to minutes and time zone conversion are things that don't really have anything to do with displaying a list. So this is stuff I can actually move over to the pre-processing I did in the background thread before I got up to the main thread. So I'm going to actually do that like right away because that's super easy to do, and that's going to get me a much better flame chart like this. Now, when I'm left, I see that my header allocation is actually still the vast majority of the work that I'm doing. So what I really want to do is take that header allocation and make it quite a bit smaller. And then I'll still leave the work for Kotlin, but it's going to be, now update schedule UI is a much, much faster method. So to do that, I have a couple different options. I can remove object allocations and make everything happen later. But I didn't want the narrative of this talk to be avoid memory allocations at all costs to get performance. So I thought instead, why don't I add another memory allocation in order to make this faster? And so what I'm going to do is I'm going to make a new class. I'm going to call it Thunk. And this is very much just a very lightweight version of lazy that's not thread safe. And as a result, gets me the performance I need. And that's OK, because I'm only calling it from the main thread. So Thunk is just going to basically take a producer. And then the first time you ask for the value, it's going to call that producer to get the value. And then it's going to return that same value from then on out. So this is a concept that you might be familiar with from Scheme, and I'm just stealing it flagrantly to implement this in Kotlin here. And when I run this again, I'm going to go ahead and measure. I'm going to measure this again, and I'm going to see that the flame chart has been updated, and I got the performance that I want. So at this point, there's a couple things that are left to do on this screen. If I was really, really, really interested in high performance on this screen, I'm still looking at something on the order of 30 milliseconds to get to first paint, which is something I might still want to optimize. So one of the obvious things to do there is, if we look at it, most of that 30 milliseconds is spent waiting for a background thread to take this list, sort it, do the index and all of that stuff. And all of that work can actually be pre-computed so that it comes out of the database in the pre-sorted order, and we don't have to do hardly as much work. So if we spend some time just to optimize that loading path, it's possible to get this down to maybe 1 or 2 milliseconds of background thread work, and then pass it right up to the UI. So that's going to get us probably the biggest win that we can get. Then past that, we can actually continue optimizing just the view layer of the screen. And I asked some engineers in Google for ideas about how to do this. And there was a kind of a bunch of different ideas that came out. There was cache the data and transformations. Then there's pre-allocate the views. Layout and draw can be basically custom done so that we can get even faster performance out of those two phases. Now, each of these comes with comes with different problems. So if I cache the data in transformations, I tend to create bespoke and difficult code. I often create curious coupling between different layers that maybe doesn't make sense at the surface, but is justified for performance reasons. So that's something to keep in mind on this one. If I pre-allocate views, the sort of solution that was proposed was something that was going to be async inflation plus the recycler view pool. This is something that's going to be fragile. It's probably going to break as recycler view version bumped because it's not a supported use case at all. So depending on how much the screen is very important to me, I may implement a solution like this, but I'm probably undertaking a lot of maintenance burden if I do so. And then I can optimize the layout and draw phase itself as well. And this is also going to be bespoke, probably very verbose code. And it also tends to be fragile based on the Android and library versions that I'm using. So I think the point of this slide is all of these things are worth doing if I really, really care about getting every millisecond out of this first load experience. But what I really want to say here is fully optimized code is often bad code. So when I think about the clean, beautiful code that's well architected and has lots of separations of concerns, often there's a lot of little performance overheads that goes into making that happen. And in order to actually optimize the code, often I have to write bespoke verbose code and kind of create weird couplings between sections that I wouldn't expect in my code base. And sometimes this can be useful, and sometimes this actually just makes bad code that runs fast, but users don't really care, which is why it's super important when you're doing performance optimization to define a goal, have a way to know when you're done doing performance optimization. All right, so that's everything I'm going to talk about in the profiling section. Now I want to wrap up by talking about benchmarking. So benchmarking library is a new library we launched last year, which is one of our internal tools that we wrapped up in a library. And its goal is to create stable performance. And there's basically two things you need to know about the benchmarking library. The first one is you really should not run benchmarks against debuggable code. And the reason for this is not because debuggable code is slower, but it's because debuggable code is unpredictably slower. So here's a couple different tests that we have, and we ran them in both debuggable and true and debuggable false, and we could see a 1% difference on one test and an 80% difference on another test. So if I use this as my baseline measurement in debuggable mode, I'm actually measuring something that's wildly different than what a user has seen, and I'm also not able to compare these things relative to each other. And then the other thing to look at here is how to kind of interpret measurements from a benchmarking library. So benchmarks tend to have noise. This is something you can get pretty tight if you really try and you focus on the code under test. But they tend to be pretty noisy. This graph you see right here is a really, really good example of a performance improvement. And you can see that just visually, there's just a lot of noise going on there. And if I tried to detect between one build and the next what the performance regression was, it would be very difficult if I only looked at 2 builds at a time. So instead, what we do is we actually use this thing called k-means clustering to figure out basically, are there 2 separate groups that have some sort of statistically interesting gap between them. So here we can see there are, in fact, 2 separate groups, and we can see that there is a performance improvement. Here, we can see that there's 2 separate groups and there's a performance regression. This is also another benchmark that you might see. This one has incredibly high variance, and there's very little information you can actually figure out from this benchmark. The most likely cause of this is there's some high variance function getting called, such as reading from the file system, which just has very unpredictable performance. So there's one last thing I want to talk about in this section, which is here I have a performance improvement. And this slide is something that when you work on performance and you come up with a performance improvement, do not show this slide to anyone. Don't show it to your product manager. Don't show it to your tech lead. Don't show it to your CEO. And the reason for that is it does not go up and to the right. So we want our slides, when we're talking about things going well, we want them to go up and to the right. So all I have to do there is just divide by one of the numbers and turn that into % speed up. And once I do that, I'm going to be able to always generate graphs that go up and to the right for performance improvements. All right, so enough slide tips. Let's talk about some code. How do I actually use the benchmarking library? So in the benchmarking library, it's basically I create a new module in Android Studio with debuggable false on it. And then I can use a benchmarking module there, and then I configure it and add it. And then benchmarking is actually expressed using unit tests. So I go into benchmarking and I'm going to find this example benchmark, which has a test log and is called log.d. And here we have benchmark rule.measure repeated. And this is the primary Kotlin API for benchmarking. And this is all you have to do. And the block in that Lambda is what you're going to actually do benchmarking of. So for this, I want to go back and look at that Bootstrap conference data source, this thing that was causing lots of work in the background thread. I want to know if that gets worse over time. Because that's something that does, in fact, eventually cause performance problems for my user, because it is eventually displayed to the screen. So I can just go ahead and use the benchmark rule measure repeated and just call the load and parse Bootstrap data in there. And this is going to repeatedly, thousands and thousands of times with lots of tricks to figure out whether it's a stable benchmark, call that function over and over again. And I can also, if I wanted to put a log in here, but I didn't want to benchmark it, I can go ahead and call another Lambda builder called run with timing disabled. And anything I put in here isn't going to be counted against my time for my benchmark. So I go ahead and run that, and we'll see the benchmark run. I hope. Well, I know it will because it's a video. And there we go. So this benchmark, by default, benchmarking spits out results to the console like this. You can also configure it to spit out XML or other sources. I believe it has a JSON output as well. So this is a really, really good way to use the benchmarking library, basically to confirm that a single code path in your application that does one task has consistent performance. I would warn you that measuring two different types of things with the benchmarking library doesn't create comparable results. So here I'm loading some JSON. If I also compared that to another JSON parser, I might be able to, if I get like a very large difference, be able to assert that maybe there's actually some difference between the performance of these. But if it's a very small difference, that's probably something that can be completely chalked up to the library just not being able to control for all of the variants. So that's wrapping up everything I had to talk about today. So thank you so much for joining, and thanks to the organizer for having me. And let's see if we have any questions.
All right. Thanks so much, Sean. That was a really enlightening talk, and I have to say that I think the only takeaway that I'll be taking back to my bosses is your statement that fully optimized code is bad code. So clearly, if we just write bad code, then it's automatically fully optimized.
That was the intention of that, really. Poor code is the way to make your code go fast.
Excellent. All right, so just a reminder to everyone, and while we're talking, I will throw this on the screen. If you have any questions, the channel in Slack is day3_Sean McQuillan. And with that, we'll get started. So Igor asks if you can suggest any ways to integrate performance profiling into the development lifecycle. For example, running regression tests on CI. And not only that, but if you would recommend doing that versus leaving this type of performance profiling for problems that users have identified.
Yeah, I think there's that's a great question, and there's basically two answers to that. A lot of performance regressions you're gonna actually work on when you're doing performance profiling like this are gonna come from some user noticed something went slow and told you about it, and you're gonna, oh, okay, let me go figure out what the slow part was. If you want to kind of capture that into CI, what you can do is you can use the benchmarking library, and that has it's a little bit of a trick to figure out how to integrate that into CI. You have to do something similar to what we did, where we look at the last 10 builds and we do that k-means clustering on it to figure out is there a regression somewhere in there, or is there a performance improvement. But it's totally doable. It's a little bit more of a project to get that put together. So there's two totally valid ways to do it. You can just respond, to performance regressions that you've been reported from users, and then you can also capture stable performance using the benchmarking library. Excellent,
thank you. It sounds like that would be a really good use case for some of those alternative output formats like JSON or XML.
Yeah. They do support the XML format that's used by Jenkins.
Oh, very cool. All right. It looks like that's all the questions that we have right now. So if you have any other questions, feel free to throw them in the Slack, and if it's too late, we can try to find a way to get a hold of Sean. But yeah, otherwise, thank you very much, Sean. Really appreciate the talk, and really enjoyed having you.
Thanks for having me. And I'll be around in chat if you have any more questions.
All right.